Hey, how's it going? Mr. Dent here. Today I'm going to be talking about position time graphs. We're in Chapter 2, Section 1. Anyway, today's objectives, we're going to interpret position time graphs to determine velocity, time, or displacement. We also want to be able to describe an object's motion based on its position time graph. And then finally, we will be constructing position time graphs when given displacement and time data. Okay, the first thing, we're going to find average velocity when we have data on a displacement time graph. Sometimes I call these position time graphs also, so please don't get confused, even though it's two different terms. And so in this case, we're going to be, we want to find the average velocity between the point from 240 seconds, which is right here, to 510 seconds. And so the way we do this, to determine an object's average velocity during a particular time frame, we want to draw a straight line between the 2 points of interest, then determine the slope of the line between the 2 points. So I've drawn a straight line in red between those 2 points, and now I just have to find the slope. Now remember, slope is going to be rise over run. So rise over run. And so rise would be the change in the vertical axis, and the run is going to be the change in the horizontal axis. So our point, our second point, or the highest point on the vertical axis of what we're looking at is going to be 1650. So 1650. Oops, need a 5. And the beginning point is going to be 1050, and these are all in meters. So meters and meters. And then that's going to be over our run, which is 510 minus 240, because this furthest point, 510, and this point right here, 240. And so we would get the difference between 1650 and 1050 is 600. And then the difference between 510, and I didn't write a 4 there, 240 is going to be 270, and that comes to 2.2 repeating meters per second. And so this would be the average velocity. Now, sometimes we will also want to be able to find the average speed from a position time graph. And to do that, we just need to total up all of the distances that were covered. And so distance, the direction the object is going doesn't matter, as opposed to displacement. We learned that before, so I'm not going to get into all of that. So we can just simply go through our graph and figure out the different distances that were covered with different segments of the line. So here would be what, 450 from here to the beginning, and then the straight line, it's not covering any new distance, so that would be 0. And then from 1050 here to 450 is going to be 600. And then 1050 to 850 is 200, because I actually went back the other way. That's what this graph is saying. So we've got 200. And again, we have a flat line, so this would be 0. And then from this point to this point, we get a bunch of little segments that create a curvature, but that's okay. We can just figure out how far it is from here to here as far as, you know, our values on our y-axis. So we got 1650 and 850. Subtract the 2, you're going to get what, 800. And so when we add all this together real quick, so I got 450 plus 600 plus 200 plus 800, and we're going to get 2050. And so remember, average speed equals 2050, or equals the total distance covered divided by the time that it took to do that. So 2050 meters, and the total time is easy. You just the furthest point and what time frame is that on, and so that's going to be 510 seconds. So 2050 divided by 510 is going to be 4.02 meters per second. All right, so that's finding average speed using a position time graph. Okay, this next part, we want to be able to identify different things on a position time graph, things that we can quickly identify based on the slope or the lack of slope, or if it's curved line, if it's upward curve, and so on and so on. Anyway, so constant motion is always going to be indicated by a slope that's that's straight versus a slope where we have a curve. Now this can be down or up, it doesn't matter. So it can be up or down, doesn't matter. Speeding up is going to be an upward curve. Just going back to that constant motion so you can just quickly see an example. So like this would be an example of constant motion. This would be an example of constant motion. And speeding up is going to be an upward curve. And so there, this would be speeding up. Slowing down is going to be the opposite. So downward curve. And then no motion, and actually is the slowing down, there isn't an example on this graph, but you can understand it's just going to be, it can be just like this, except it'll go down. Okay, no motion is going to be a flat line, so flat line. And then change direction would be like this right here, where we have an upward slope and then suddenly we have a downward slope. So we could say upslope, and then suddenly we have a downslope. Let's see, instantaneous speed. Instantaneous speed, we have a particular way that we find instantaneous speed. And so the way we do that is we draw a tangent. So we're going to draw a tangent that just skims the point of interest. So in this example, we'd be at 450 seconds. We want to know how fast we're going at this spot right here. Whoops, my arrow's not exactly right. But right here at 450 excuse me, seconds. So we would draw a tangent line that just barely skims this. So I'll just write that real briefly, draw a tangent line. That just touches point. And then we would find the slope. So in this case, and I don't want to make this last too long. So here's my tangent line, and I found my slope with with these numbers. So I picked a point at 1500 meters as the upper point, and then my lower point on the y-axis was at 800 meters. And then I picked out 510 seconds. Whoops, I need a 1. And then we had 400 seconds. And that gives us 700 over 110, which gives us a slope of 6.36 meters per second for the velocity that was occurring at that particular moment in time. And so this would be instantaneous speed, where we would find that using a distance time graph. Last thing we're going to talk about is making position time graphs. So usually I'll give you the data in a word problem, so this is going to be a lot easier. Like what I'm showing you is just once we have those numbers. And just in the interest of saving time, I've already done that. And so you're going to have to figure out how to do that, and you can talk to me as you do some of the problems, and you'll be able to figure that out. That's not going to be a problem. But first thing, we want to label everything. So we have time on the x-axis and displacement on the y-axis. And then we'd also label our axis as far as giving values. So 1, 2, 3, 4, 5. I'm just going to label every 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 2, 3, 4. And that's all we need because we only go up to 11.5 on time. And then for the y-axis, I'm making each box worth 5 because we need to get up to 100, and we don't have 100 boxes. So yeah, and that's something you have to do when you're doing these by hand. Most of the time I'm going to have you make these on Excel, so it'll be a lot easier. So 40, actually that's going to be 4. Screwed that up, didn't I? So 20, 2, 3, 4, 5, 40, 2, 3, 4, 4, 60, 80. Okay, so we have everything labeled, and for as far as a label for the graph itself, we could just put displacement versus time. And if you knew some information about the objects, then you could add that too. So real quick, so just plot your point just like you do any other graph. 0, 0, 2.5, so 1, 2.5, and we were at 20. Then at 5 seconds we were at 45. Then at 7.5 seconds we were at 67, so there would be 65, and about there maybe. Then at 9 seconds we were at 85, and then at 11.5 we were at the 100-meter mark. So if you were to, connect these dots, with somewhat, and I know these aren't super straight lines, then that's what you would do if you're doing this by hand. Get a ruler out and draw lines, but I don't have a ruler that'll work with this pen pad, I don't think. never tried it actually. So you connect your dots, and as you can see, it's not a perfectly slope. It's not a perfectly straight slope. So that means we probably do have, this isn't constant velocity for the entire time. And since this is a 100-meter dash times, that makes sense. They'll start out at one velocity, go, and then they'll speed up and then kind of slow down at the end. Anyway, that's how you make a position time graph. As far as assignment goes, you have a worksheet, worksheet 2A1, displacement time graphs, and then you will be ready for the quiz over section 1. This concludes this screencast. I hope you enjoyed watching the screencast as much as I enjoyed making the screencast. See you in class.